Writing code is the act of commanding physical hardware. Every time a Java program runs, the operating system yields a precise fraction of the computer's physical memory for the application to consume and manipulate. To harness that memory, developers use variables. At its bedrock, a variable is simply a reserved storage location within that digital space. When a variable is declared, the JVM allocates a very specific quantity of memory to that slot, locking in the width. The program then binds this physical address to a human-readable identifier, allowing the developer to retrieve and modify the data. Because these labels are bound to specific addresses rather than the code itself, Java effectively decouples an application's state from its execution logic. The methods provide the behavior, while the variables serve as a distinct structural layer where the object's internal state is protected and preserved. Mastering Java requires mapping this exact physical architecture. A developer must know exactly how a data type dictates the memory footprint, and how a variable's physical location dictates its lifespan. Every piece of data in Java is classified by a strict binary divide. A variable is either a primitive type or a reference type. On the left, primitive types hold raw, exact data directly within their memory slot. On the right, reference types behave entirely differently. Instead of holding actual data, they hold a memory address, a pointer, to a dynamically allocated object living elsewhere. This chart outlines the precise mathematical boundaries for the integral primitives. Because primitive variables hold data directly, their maximum values are strictly bound by their bit width. An 8-bit byte can never exceed 127. The 32-bit int serves as the standard default for integer calculations, providing a range of roughly positive to negative 2 billion. When a calculation requires a wider range, the 64-bit long is deployed. Further down this specification chart, we see the remaining primitives: the float and double for decimal precision, the 16-bit char for single Unicode characters, and the boolean flag, representing a pure true or false state. Reference variables, which handle strings, arrays, and class objects, bypass these strict internal size limits. By storing only the address of the data, the reference variable itself remains lightweight. This provides a specific architectural advantage. Multiple variables across an application can point to the exact same object on the heap without duplicating the underlying data. A variable's data type exclusively answers two questions for the JVM. How big is the required memory slot, and does it hold a raw value or a pointer? Beyond its type, a variable is defined by where it is created. The first major category is the local variable, which tracks temporary execution state. Local variables live on the JVM thread stack. When a method opens, an execution frame slides down, populating with local variables. This lifecycle is highly volatile. The variable is born when execution enters the block and is instantly destroyed when execution exits. Because of this rapid creation and destruction, local variables are completely invisible to the rest of the class. They exist solely to process immediate logic. This temporary stack memory introduces a risk. If a local variable is declared but left empty, reading it would risk returning leftover garbage data from a previous operation. To prevent memory corruption, Java enforces the definite assignment protocol. The compiler actively scans the code, and if a local variable is used before it is explicitly initialized, the program will fatally fail to compile. Local variables are intentionally short-lived and subjected to strict compiler checks. This guarantees execution logic remains fast, contained, and safe from unpredictable memory reads. Outside the tight confines of the execution stack lies the JVM heap, a vast, persistent memory space designed for long-term storage. This is the home of instance variables, also known as non-static fields. These are declared inside a class and hold the independent, persistent state of an individual object. Instantiating objects from a class blueprint carves out isolated memory slots on the heap for each object's instance variables. Because they're physically bound to a specific object, they can only be modified through an active reference to that exact instance. Unlike local variables on the stack, instance variables do not require explicit assignment to pass the compiler. Instead, the JVM automatically grants them default values upon creation: 0 for numeric types, false for booleans, and null for reference types. The compiler applies these defaults because the JVM cannot risk abandoning massive objects on the persistent heap, filled with raw, uninitialized memory. Pre-filling them with a neutral state ensures systemic stability. Through this mechanism, instance variables establish the distinct, persistent identity of an object, safely isolated from both the temporary execution stack and the data of every other object on the heap. The final major category is the static variable, or class variable. These represent shared global state across an entire application. Architecturally, there's exactly one copy of a static variable in memory. Even with 10,000 instantiated objects, all look to a single shared storage location. They don't require an object to exist, and are accessed directly via the class name. For years, developers debated where these global variables physically resided, often confusing them with structural class metadata, which is stored in native metaspace. In the modern JVM, static variables live on the heap. The JVM creates a specialized java.lang class object to store them. Pushing them here ensures they are managed by standard garbage collection, keeping the native metaspace reserved purely for structural metadata. Static variables intentionally break the rules of object isolation, serving as a controlled, necessary bridge for data that must be accessed globally. The JVM strictly dictates how variables are physically stored, but human engineers dictate how those variables are organized and read. Java requires compliance with absolute lexical rules, like case sensitivity and the avoidance of reserved keywords. But beyond the compiler, professional development relies heavily on community-driven naming conventions. Code must be self-documenting. Standard practice requires camel case for variables and methods, Pascal case for classes, and the strict avoidance of cryptic single-letter abbreviations outside of temporary loop counters. The singular exception to this formatting applies to constants. Variables marked with the static and final modifiers are written in all uppercase letters, separated by underscores. When combined, these elements form a unified architecture. The stack rapidly pushes and pops local variables, while the heap permanently anchors instance and static variables. The data type determines the size, while the classification determines its lifespan, scope, and initialization. A developer who masters these tiers of storage can precisely predict the memory footprint and the operational lifecycle of every data point in their application. This architectural knowledge is what allows you to move beyond simple syntax and truly control the runtime environment of the JVM.